In this final video on k-nearest neighbor, we will talk about one variant of the algorithm and an advanced method that can be considered an extension of k-nearest neighbor. For the probabilistic interpretation of k and n, we take a closer look at how our data was generated. We assume that our data has been generated from a combination of several multivariate Gaussians and model this by placing a multivariate Gaussian over each data point, and then use these Gaussians, which use our data points as the means, to derive a generative model for our data. So knowing that our class that we are looking at is class C, the probability that the data point x is being generated is the average over all of the Gaussians that use data points from class C as the mean values. Like I said, here we are trying to model the way that the data has been generated. This is in contrast to before, where we have created a discriminative model. If we take a look at the plots for the generative models for classes red, blue, and green for our toy example, then we can see that it is regarded much more likely that a certain point of a certain class has been generated by our model if it's surrounded by a lot of points of that class. We can probably understand a little bit better what's happening here by looking at an example where we have one-dimensional data points. So right here we have 5 data points, and we assume that they all belong to the same class, and do the same that we did before. We center a Gaussian distribution on each of the data points. They use the data point as the mean, and here we use variance 1. But sigma squared is actually a hyperparameter of this method. You can see that a point x is much more likely if it's somewhere in between or around these data points right here. We can use these generative models to go back to our original goal, and that was to classify new unseen points. We do this by simply applying Bayes' rule, and find out that the probability that the class label should be C for a new unseen point is proportional to the probability that it has been generated, given that we know it has class C, times the overall probability for class C. Now doing what we did before, by taking the arc maximum over all possible classes, we can find out what this new data point should be classified as. Let's move on to a more advanced method. In neighborhood component analysis, or NCA, we also perform k and n, but instead of completely defining the distance metric for k and n beforehand, here we restrict ourselves to the Mahalanobis distance and try to find a good matrix Q to use in that distance measure. Like I said before, Mahalanobis distance is essentially Euclidean distance after applying a linear transformation. And we can see why that is here. Due to some of the conditions we need Q to fulfill in order for this equation to be actually a metric, we can find a matrix A so that Q can be computed by the matrix product of the transposed version of A times A. So we can rewrite Mahalanobis distance in this way right here, and that is equal to using Euclidean distance between these two vectors. So actually we can make our life a little bit easier and not learn Q, but learn a good A. The question of what a good metric is still remains though. And we can define this by saying that if we use matrix A and we take one example from our training set and try to classify it based on all of the other training examples, which is essentially leave one out cross-validation, then that single training point should be classified into its known class. Unfortunately, if we do it this way, the classification performance is not a continuous function of matrix A. Since the neighborhood of one point is something very discrete, some small change in matrix A can cause the neighborhood to be completely different, even if there's just one neighbor that changes. So even though A just has changed by a tiny amount, our classification performance might jump in some direction. We can do a little better by using a different performance measure. We still want to do leave one out cross-validation, but instead of assigning the class directly, we use probabilities. We define a probability for points I and j, so that point I selects another point j as its neighbor by some probability pij. Obviously, a point cannot be a neighbor of itself, so pii is equal to 0. And this expression, which is a softmax or normalized exponential, ensures that all of our probabilities will be between 0 and 1, and that the sum for one point e is equal to 1 as well. It also leads to higher probability for points that are close, according to the current distance measure a, and lower probability for points that are very far away. The probability that we correctly classify point I is then given by the sum over these neighborhood probabilities if we just choose the neighbors that have the same class as our point I. Finally, we can use this to maximize the expected number of correctly classified points. This function right here gives us an objective that solely depends on A. So in order to maximize it, we can just use gradient ascent, and by that find a good value for A. The gradient for the function f with respect to the matrix A looks a bit complicated, and you will take a look at how this is exactly computed in the tutorials. The algorithm also learns an estimate of the optimal number of neighbors. The method consults fewer neighbors if we scale A up uniformly, and more neighbors if A is scaled down. There is another nice side effect to this method, and that is if we use a non-square matrix A with one dimension lower than the number of dimensions of our data, which essentially means that we are using Euclidean distance in some kind of lower dimensional space, we can use the same matrix to do dimensionality reduction. This works because by restricting the matrix A in this way, we force the algorithm to find some kind of lower dimensional embedding of the data, where our Euclidean distance can help us to get a good expected number of correctly classified points. You can see some results on this slide. On the top left, we used NCA on a dataset with 5 classes, and the original data was 3D and contained concentric rings in 2 dimensions. However, the third dimension was Gaussian noise of high variance. The data in the lower left was originally 13 dimensions, and this is a wine dataset where different wines are classified into 3 classes according to some attributes. On the top right, we performed NCA on face data, which means that in the dataset there are 18 different people, and we have about 100 images for each person. And you can see that the algorithm actually finds some embedding where the faces for one person are close to each other. Finally, in this image, you can see the result of dimensionality reduction with NCA for digits. And here we used some handwritten digits from 1 to 5. And NCA also yields a quite nice result in this case. Since these 4 figures are taken from the original paper on NCA, when I said we, I kind of actually meant the authors of the original paper. So this concludes the lecture on the k-nearest neighbor algorithm. Let's summarize real quick what we talked about. We first looked into the algorithm itself. Then we discussed cross-validation for choosing the parameter k. Then we looked a little bit into the second choice that we have in k and n, which is the distance metric. And finally, we discussed a very common problem in machine learning, which is the curse of dimensionality, and talked about some variants and extensions of the k and n algorithm.